This is a re-upload of the video I had uploaded earlier. This is a corrected version of this that had some errors in it, which is on probabilistic coding, which uses conditional probability for calculating the probability of a large sequence. It could be a sequence of text. Typically, I'm just assuming bytes here, but it could be anything. It could also be adopted to be based on the convention in which, or the language in which the symbols are taken. If it is a language where you convention is to read from left to right, we can code it from left to right, or if it is from right to left, we can code it from right to left. Now, before proceeding, since it is customary, if you like the videos you are watching, please subscribe to the channel. But none of these videos, I must mention, are meant to, methods that I have outlined here are meant to be used for commercial purposes in order to make money. But this is a very, very computation intensive method, and it, as to whether it really represents a data compression method or a data error detection and correction method, it can be used for either case. So it is a borderline or either case you get for compression, but it involves, it also is an illustration of the trade-off that is often involved in computation, where you can save on memory space if you are willing to perform a little bit of extra computation, in which case you can actually losslessly compress code it. So while trying to solve one problem, if you try to solve the problem of data compression, you will also obtain insight into solving the problem for data error detection and correction. And if you try to solve the problem for data error detection and correction, you will obtain insight for performing data compression. So these two are very closely related to each other. Now, in order, since we are making use of conditional probability, we just brush through that formula for conditional probability. So for probability, it's best to use a Venn diagram. If S is a sample set, finite sample set, A is any finite subset of that sample set, then cardinality of A over cardinality of S equal to probability of occurrence of event A. And likewise, if we have a finite sample space, for conditional probability, what is the probability if this is A is a subset and B are subsets and S is a finite sample space? Given that A has already occurred, what is the probability that B now occurs is nothing but cardinality of probability of B, given that A has already occurred, is equal to cardinality of A intersection B by cardinality of A. Now, in order to draw Venn diagrams, you can make use of the simple fact for larger number of sets such as 4 and 5 and all that. For two sets, if we take the centers of the circles to be endpoints in the line, the radius you have to take will be slightly more than half. Likewise, you can locate the sets at the endpoints, vertices of an equilateral triangle, and this length of the side, again you have to take the radius to be slightly more than half the length of each of the side. For 4 sets, again you will have to locate the circles at the endpoints of the square, and if the side of the square is again, the radius of the circle should be slightly more than half the midpoint of the side of the square, and so on. You can keep extending it. So the idea of using Venn diagrams is a good idea because it gives you a clear picture of what you're dealing with here. So, and what each of those sets represents, and how do you determine those sets or calculate those sets in terms of their union and intersection or any other way of calculating it. Now, basically, now what we have here is a finite alphabet consisting of n symbols a0, a1, a2, an minus 1, and a huge body of data or a stream of data of length L dash. Say I will take only a few symbols here, ai0, ai1, ai2 and ai3 and so on up to ai L dash minus 1, where L dash is very, very large. Okay. So this is the data stream we wish to code. And what we do is initially we count the occurrences of a0 in this body of text and a1, a2 and so on, and maintain a table of n elements. Then we maintain another table of n square elements. What we do is we pair ai this in this, this in this, this and this for up to L dash minus 1 pairs will be there. For each of those elements in this pair, we maintain a table of square n square. So whichever is the element there, cardinality and number of occurrences of each of those also we maintain. So n and n square. Now we are interested in this. If we, from these two tables, we can, for instance, we can easily compute what is the cardinality that ai1 occurs in the sequence given that ai0 has already occurred. This is nothing but ai0 comma ai1 by summation of all ai0 comma x, where x belongs to the symbol. So this is the probability that we know for this, but we are now interested, from these two tables we can always calculate this probability. But now we are interested in extending this to 3 symbols instead of 2. Is it possible? So we should see if we can do that using just those 2 symbols. Is it possible to obtain the probability that ai2 occurs given that ai0, ai1 has occurred? We are interested in this now for this. So if we have to try to calculate this probability. For that particular text, since the convention is from, I'm assuming a left to right convention, you can assume, so probability that for this triple ai2 is equal to probability that ai2 occurs given that ai0, ai1 occurs. This is again nothing but ai0, ai1, ai2 by summation of all ai0, ai1 x, where x belongs to the alphabet. That is, we are interested in, see if we can calculate for the triple based on the pair alone. Okay. Now what we have there here is, we are interested in ai2 occurring given that ai0 comma ai1 has occurred is equal to ai0 comma ai1 plus ai1 comma ai2 minus ai2 naught given that plus AI2 given that A not this is similar to the principle of inclusion and exclusion, basically that only. So if we want to know the cardinality where AI2 occurs whenever AI0 and AI1 has occurred, we take the cardinality of sum of cardinality AI0 and AI1 has occurred and AI1 and AI2 has occurred. But from that we have to subtract the case where AI2 does not occur when AI1 not occurs, AI1 occurs, as well as the case where AI2 occurs whenever AI not does not occur but AI1 occurs. Because since we are for this case where we are assuming here AI1, AI2 has occurred, but it's possible that AI not has not occurred. So that part has to be subtracted there. Those cardinalities have to be subtracted here from these two sums. So this part is there. Now we can see if we can calculate this sum. If we can do, then we can always obtain the probability that AI0, AI1, AI2 occurs. Given that, so our objective is to obtain this sum from the existing information so that we can accurately calculate that probability. Now I shall consider, therefore we have in this triple here AI0, AI1 and AI2. I shall consider the middle thing here AI1. I have AI1 is equal to AI0 comma AI1 plus naught of AI0 comma AI1 is nothing but summation of x comma AI1, where x belongs to A. But I am only interested in AI1's occurrence relative to AI0 as well as AI1's occurrence relative to not AI, all the others rest. I am splitting it into those two parts. Similarly, we can also let this value be equal to t AI1. So similarly for this also we can split it relative of occurrence relative to its right on AI2, and we can say AI1 comma AI2 plus AI1 comma not AI2. Okay, here it is preceded by x, or we can take AI1 here and succeeded by. Assuming now that AI1 does not happen to be the first element or the last element. That is an assumption. Those two cases are there where you must be able to add at least 1 or 2 to the formula in the case. Those must be excluded as not considered here. Those exceptions, if they do occur, there are just only 2 possibilities here. One of those 2 possibilities. In other words, 3. Either it occurs only in the first symbol but it does not occur in the last. It occurs in the last symbol, does not occur in the first, or it occurs both in the first and last. Which 2 cases values, depending on that, if that does happen. For some symbol that will definitely happen. You just have to add 1 or 2 to the formula. So basically the picture we have here, roughly, we have AI1 here. not of AI not AI1, AI not AI1, AI1, AI2, AI1 not of AI2. So we have to see if we can deduce that from this available information, if we can deduce it for the triple case AI not AI1, AI2. So based just on those two tables. Now I have here, let U is equal to AI naught comma AI1 is equal to cardinality of all AI2 given that AI naught comma AI1. Okay, plus AI2 not AI2, AI not AI1. Okay, I'll call this equal to A plus B. Okay, that is similar to what we did for that, but now we are taking for the pair here. This is AI not AI1 here. That is AI2 occurs given that AI not AI1 occurs. AI2 does not occur given that AI not AI1 occurs. This I am calling A and this I am calling B. And this itself I am calling U. And V equal to AI not does not occur given that AI1 occurs is equal to AI2 occurs given that AI not does not occur but AI1 occurs plus AI2 does not occur given that AI not does not occur comma AI1 occurs. Okay, so this I am calling B, this part again, this part I am calling C plus D. In other words, this term I am calling C and this term I am calling D. Okay, so in general we will have this. So we will have A plus B plus C plus D is equal to T, or T is equal to A plus B plus C plus D, and U is equal to A plus B, V is equal to C plus D. Okay. Now I will assume A plus C equal to X and B plus D equal to Y. But what does A plus C represent? Which can become from that binary table itself, you can calculate. It is nothing but A plus C is equal to table of all AI1 comma AI, occurrence of all AI1 comma AI2, and B plus D is equal to occurrence of all AI1 comma not of not of occurrence of AI2. Okay, this can be obtained from the table A plus C and B plus D. Okay, that is just this is a summation here where you exclude this element. This one you can directly read from the table. This one, summation of all of that excluding this one. Okay, so A plus C and B plus D, I am calling it X and Y, which can be directly obtained from this table. Now from the formula we have A is equal to AI naught AI1 plus AI1 AI2 minus B plus C. Now this can be written as A is equal to AI naught AI1 plus AI1 AI2 minus T minus A plus D. Sorry, A plus D. Okay, so A and A will cancel out and we will obtain D equal to T minus AI naught AI1 plus AI1 AI2. Okay, so we will obtain that. Okay, and furthermore we also, from those four equations we have B minus C is equal to U minus X and A minus D equal to X minus V. This also you will obtain. Okay, from those earlier equations we can get this as well. So if we know D, we can know A, and all. Similarly we can find out A, B, C, D, all of them. All of those values can be found out. So we can clearly find out the occurrence of probability, or the number of occurrences where I2 occurs whenever AI0 and AI1 has occurred. We can do this also. Now similarly we can extend this to see, now that we know for 1 and 2 and 3 as well. See, we can similarly, the same like manner we can extend it for 4 also. What is the probability that AI4 occurs given that AI0, AI1, AI3 occurs, given that AI0, AI1, AI2 has occurred for 4 elements. AI3 given that AI0, AI1, AI2 has occurred. Okay, so I'll just quickly go through that. It will come to the same thing only. So in similar like manner we can extend it for 5, 6, 7. So in other words, just if you have the table for 1 and 2, we can, for a given data stream, we can calculate these probabilities automatically. So we will have AI0, AI1, AI1, AI2, AI3 is equal to AI0, AI1, AI2 is nothing but this. So we will obtain AI0, AI1, AI2 is equal to or rather directly to write it this way, AI naught, AI1, AI2, AI3 is equal to AI naught plus, AI naught, AI1, AI2, AI2 plus AI1, AI2, AI3 minus cardinality where AI3 does not occur, given that AI0, AI1, AI2 has occurred, plus AI3 has occurred, given that AI0 has not occurred, AI1, AI2 has occurred. Right? Now for the three cases, we know all these probabilities. If we have that, we are able to later construct a table or whatever is necessary for each of these symbols. Then we can always calculate for 4 of these, again similar to this. Okay, here we are taking away the cardinal, like just we did for the binary case, or for 3 elements, so also for we are doing for 4 elements now. The same thing only. Therefore we have, now we assume rather than there we took AI1 to be T, now we will be taking the pair AI1, AI2 to be equal to T. So this will be equal to AI0, AI1, AI2 plus AI0 not dash AI1, AI2. Alternatively, this will be equal to AI1, AI2, AI3 plus AI1, AI2 not AI3. That is, every other element comes here, sum of all of that other than AI3. Okay. And similarly, we can have U is equal to AI1, AI2, AI3 is equal to AI3 given that AI0, AI1, AI2 plus not AI3 given AI0, AI1, AI2. Okay, this is we have here. This part I am calling as A, and this one I am calling as B. Plus AI3 occurs where not of AI0 does not occur. This will be AI naught, AI1, sorry, AI naught, AI1, AI2. And similarly we have AI naught does not occur, AI1, AI2 is equal to this, I am calling it V equal to where case where AI3 occurs, given that AI naught, AI1, AI2 occurs, plus the case where AI3 does not occur, given AI naught does not occur, AI1, AI2. Okay, so similar to the for the binary case of three elements were taken. Now here 4, for this you have to take this, and then again we will have T equal to A plus B plus C plus D, and U equal to A plus B, V equal to C plus D, and A plus C equal to X. I will again assume that for the three elements you have the entire table there, so you know you are able to calculate X independently from that table. You can constructed it for 3 elements from based on the table of 1 and 2 elements. So you have able to construct it for 3 elements and so on. So you can get B plus D equal to Y. If not for anything else, if you are able to calculate this probability, given you can accurately determine whether the for error detection correction, this will be immensely helpful. You can also use it for decoding it and reconstructing the entire message back again, if you are able to. But it will take a lot of memory space when you expand it and build those tables. It will take time, but once you use those tables and compress the information code itself will be compressed to a very small value. But from the small value you should be able to recover the original messages, information on the data stream itself. But to do so you will require a lot of memory now, because even though that message is also large, the table required for constructing it will also be fairly large, but the message can be accurately recovered. So similar to for the case for 3 elements, we can solve for 4 as well, and so we can calculate the entire probability, right? So given any particular string, data string for a reasonable length, what is the probability that from this for that particular stream, if you calculate the probability like this and store that probability, even though the tables, either the tables match the number of sequences where the number of occurrences, n occurrences and n square occurrences match, yet the probabilities matching will be virtually 0, because if you calculate the probability accurate enough to n number of bits, to a reasonable number of bits, and store only those bits, and along with this table you have essentially stored the entire information correctly, which can be used later either for correcting if there are any errors in the information to correct it, or as some kind of an image, disk image or a stream image, you wish to compactly code it so that it can be used for later correcting it. But this will take a lot of bit of computation time. So once in a while, or not too infrequently or not too frequently, when you have the time, you can use these kinds of methods for storing the entire disk compactly in, so that it can be used either for error detection and correction or for complete data recovery.